So what I want to talk about today is how we can achieve quantitatively accurate lithium-sulfur battery models. But first, why lithium-sulfur? So just as kind of a very, very brief overview of some of the potential upsides of lithium-sulfur batteries, is a higher level of expected practical energy density. So that's 700 watt hours per kilogram as compared to lithium ion cells, which are around 210 watt hours per kilogram. We have a potential lowering in costs of the actual materials used, and those materials should be less harmful to the environment. And we also get low temperature applications already being tested, and the cells seem to work over a good range of temperatures. However, and this is part of the problem I'm trying to solve, is the electrochemistry and various mechanisms inside the cells are far from established. So part of my job as a modeler is to translate some of the hypotheses from experimental data into mathematical form, and we can test these hypotheses by seeing what predictions those hypotheses in mathematics give. This is part of a larger set of kind of modeling ethos that we outlined in the 2021 roadmap. So it's quite a large document about lithium-sulfur batteries. And what we're pushing for here is, one, open access. So we want our models to be available to any and all researchers, and we're doing this by publishing some of our models, both past and present, into PyBaMM, as well as trying to create a testing framework which is a lot more rigorous than what is currently available in the literature. So in terms of testing, something that we need to do is, and that we are doing with the current model, is we need to consider what is the application for the model. Now, typically what we're going to have is a limited set of data, and that we're going to fit the model to, and we're going to try to predict future behavior in a particular application. So we have some future unknown behaviors of the cell that we want to predict, and in order to test whether a model is good or not at doing that job, what we're going to do is we're going to take the set of data that we do have for some experiment, and we're going to split it up into some known data used to fit the model, and then known data that we can use to test the capacity of the model to predict unobserved behaviors, unobserved relative to what was used in the model development process. And not only do we want to make this testing procedure a lot more common, but we also want to test a wider variety of features than is currently tested, simply so that when we come across a model selection problem in an application, we can kind of have a better apples to apples comparison of which model is perhaps better suited to some particular application. And so if we have many different types of testing procedures, we can actually start to distinguish which models actually differ from one another. And part of this came out of looking at the literature and observing, if we look at some of the behaviors or some of the operational loads we can perform on the cell for physics-based cell level models at the continuum level, we can look at the discharge curve, voltage curve, charge voltage curve, the cycling over voltage curves, also ohmic resistance, and some rate capacity effects, rate capacity effects for charge and discharge. And what you'll notice is that it's quite sparse in the literature what is actually being tested, and not only that, it's clustered. There's quite a lot that's left untested, even though all of these models illustrated here have the capacity to perform these simulations. And so we come across this problem where we have a wide variety of models which have, let's say, a claim to a discharge voltage curve, a good prediction for discharge voltage curve, but we cannot really distinguish between the models which have a wide variety of complexity. So they may be difficult computationally or elsewise for an application. And so part of the task we're doing here is to have a wide variety of simulations so that when it comes time for an application, we can actually state where our model is good, where it is not good, and that's going to lead to future development by being a little bit more open with the quality of the model. So the electrochemical pathway that we've chosen, and again, the actual pathways are not precisely specified with experimental data yet, but we've chosen the simplest pathway, which gives us the results that we believe are good for this level of simplicity. Is we start with S8, a neutral species of polysulfides, which then go through various electrochemical reactions to reduce the order of the polysulfide. So down to S4, from S4 to S2, from S2 to S1, and then S1 precipitates. And what this will give us with a zero-dimensional model is a dynamic system. And although this might look quite complicated, this is actually one of the simpler models that we have available to us. And we have within the reaction kinetics, we have Butler-Volmer reactions with Nernst potentials. We have a fairly straightforward precipitation model, as well as a pseudospatial feature for what's called the shuttle phenomenon. And that's a phenomenon I'll talk about in a little bit. So the first thing we need to do is, of course, validate the model against experimental data. So we have the experimental data from Hunt et al. 2017. And we observe that we actually get very good quantitative agreement between a charge curve, which is the solid line, and the experimental data, which is the dashed line. We can further this in-sample validation for resistance data. And again, we get, for such a simple model, a fairly good agreement between the resistance data and the experimental data. Not all models, especially ones of a high degree of complexity and sophistication, can actually achieve this level of accuracy. So that's quite good for the model at hand. The discharge curve, the discharge voltage curve, when compared against the experiment, is not as good as we would like. That being said, this is actually quite a common feature when fitting data to the charge curve and the charge data. And so there's some further mechanisms that we need to include into the model to make this a little bit more accurate. And finally, we have the actual out-of-sample prediction. So this is a true prediction where none of the simulation data that is presented here was actually manipulated in any way from the experimental data. So this is what would be observed in application, is how well does the simulation actually achieve what is actually observed, the experimental data. And so, of course, there is some error, but we definitely get the correct trends that we would hope for, as well as a fairly good quantitative prediction for the resistance data. And this is for a discharge resistance curve. And so that certainly bodes well for the model. But we can take this further by simulating this over different constant temperatures. So the data is from a single layer cell, which is held at a constant temperature. And so this is discharge behavior across 3 different temperatures. And again, we get fairly good quantitative agreement between the experimental data and the model. And again, this is in a purely kind of what we would expect to happen during a true application. We also can predict what should happen in alternative scenarios. So we don't have specific data from the experiment that we used in the previous slides, but there are general trends across lithium-sulfur cells that we can try to highlight and see if our model predicts those behaviors. So one of the behaviors, for example, is if you were to discharge at a lower discharge rate, then you would see an increase in overpotential and an increase in capacity. So we get one of two here. The capacity effect is strictly due to the simplicity of the model, and there's some extra mechanisms that we need to include in order to capture this. But that's also a good hint that with this wider array of testing, we can see precisely where the model it has shortcomings, but also where it is good. Like I said, we have this pseudospatial feature, which is to capture the shuttle phenomenon. And essentially, there is a transport phenomenon which will self-discharge the cell. So if the charging current is low enough, the self-discharge rate will equal that of the charging rate, and you'll get this apparent infinite capacity effect. Alternatively, if the discharge rate is high enough, you'll get an end of charge voltage spike, which will be cut off due to the operating limits of the experiment. And so we do indeed observe that, and it's not clear whether the data in the experiment that we used for the model actually observes that at the low C rate of 0.1. We also get some predictions for cycling, so we don't have any degradation features, and so naturally we don't get necessarily the cycling degradation that we would expect from a true cell. But we do get some of it, and this definitely bodes well for just setting the correct initial conditions for the system, which is something we don't fully have. And finally, there's a feature called the charge kink, which we don't get, and essentially this is a feature where if you discharge a cell a great amount, you'll get a spike in the initial voltage, and there are certain mechanisms which could produce this, and the fact that our model doesn't produce this is very illustrative of why this may or may not occur. So to conclude, we built a minimal model, so something that is far less complex than what is currently out there for a wide variety of the models. We capture many of the typical features of lithium-sulfur cells, and we also get quantitatively accurate predictions for some features such as resistance. The code that we've written this in is the open source PyBaMM, so it will be available to all developers to tweak as they wish. And the full gamut of model testing will allow us to really pinpoint where the model is correct and incorrect. Thank you.